Hi everybody. So now let's start the lecture. So for this part, so this is for the graduate student, for the EC635 student. For those NE353 students, you don't have to go through this slide because you have already taken NE343 microfabrication. But I know that for many EC635 students, they haven't taken similar courses. So this slide will give overview of the microfabrication. So we will cover about lithography, thin film deposition, and etching. Actually, there are also other topics like how to grow silicon wafer, diffusion doping, ion implantation, oxidation. But those components are not as important as the lithography, thin film deposition, and etching. That's why I will only cover those three topics. So I covered here because the microfabrication is the basics for the nanofabrication. If you want to do nanofabrication, so you should know something about microfabrication. That's why I gave the lecture here. So here is a simple example of the microfabrication process. So in this case, what do you want? You want to make the MOSFET. This is the MOSFET, metal oxide semiconductor field effect transistors. So you have the source, drain, and you have the gate, and also you have the metal interconnection, and you have this isolation oxide. So this one looks complicated, but actually, so all the micro or nanofabrication consists of the main three components. That is the first, lithography. So the lithography determines the lateral size of the feature. For example, for the gate, if the gate is 7 nanometer, this process is determined. The 7 nanometer is determined by the lithography process. So in the lithography process, it generates the pattern in a material called resist. So here we talk about photolithography. So later on, we will also talk about electron beam lithography, non-imprinted lithography, focused ion beam, and many other lithography techniques. So again, the lithography determines how wide, how big is the structure. The next component is the thin film deposition. This is additive process because you add material to the substrate. For instance, if we look at here, the gate material. So in for the MOSFET before maybe 10 years ago, the gate material is polysilicon, polycrystalline silicon. But this polysilicon is coated by the thin film deposition process. So this includes a chemical vapor deposition, physical vapor deposition, which for the physical vapor deposition it includes sputtering, evaporation, and there is also electroplating, molecular beam epitaxy, and other deposition process. So the third component is etching process, is subtractive process, which includes plasma etching, that is reactive ion etching or ICP etching, ion beam etching, wet chemical etching, and polishing. For the case of the semiconductor devices, we also need doping. So normally the doping is done by the ion implantation, or it can also be done by a high temperature diffusion doping process. So for the etching, it is a subtractive process. For instance, so we will deposit the polysilicon gate material, and it will be coated everywhere. Everywhere you have polysilicon. Then you do the lithography, so you remove the polysilicon here and you remove the polysilicon here by this etching process. So here I give you a simple example of the micro or nanofabrication process. So in this case, what do we want? We want just a simple metal structures. So this can be used, for example, to measure the electrical property of the carbon nanotube. Carbon nanotube. If we want to measure electrical property of the carbon nanotube, so you can have the carbon nanotube. You put one electrode here and one electrode here. So this is the process. So there are two processes to pattern those metal nanostructures. So the first one is called the direct etch process. So in this process, so first we have the substrate. We coat the metal film. This is the metal film. Then we coat the resist. Then we do the lithography to pattern the resist. Then we use the resist as the etching mask to etch into the metal. Then we remove the resist. In the end, we get the metal structures. The second process is called a lift-off process. For the lift-off process, so we coat the resist first. Then we pattern the resist by the lithography process. Then we coat the metal. So the metal will be coated on the top and also on the bottom of the resist. Then we dissolve the green color resist. So when the resist is dissolved by the solvent, the metal on top will also be dissolved. So you leave behind the metal structure on top of the substrate. This is also what we want. So those are the two basic pattern transferring process. You transfer the pattern from the resist to the metal layer. So now let's look at photolithography. So there are three modes of the optical lithography. The first one is the simplest one. It's called contact printing. So you just put your mask on top of the photoresist, then you shine the UV light, ultraviolet light. So the good thing for this is that you have very high resolution. You can get really, really high resolution because there is no light diffraction. But the problem is the mask wear and defect. Because you have the mask right on top of the resist, the mask will be contaminated, and also there may be some dust particle trapped in between. To reduce this contamination, you can keep a gap between the mask and the resist. But again, sometimes it will happen that the mask will be in contact with the resist because the gap has to be small. If we have too big a gap, the resolution will be poor. So the gap is just a few micrometer or maybe a few tens of micrometer. So by chance, the mask can still be contaminated. And also, because you have the gap, the resolution will be lower. So what do you think is the resolution for this proximity printing? So we know that the resolution will depend on the wavelength. Resolution will depend on the wavelength. It also depends on the gap. And obviously, the bigger the gap, the bigger the feature size, the lower the resolution. And also, longer wavelengths, bigger feature size, lower resolution. So in the end, actually, the formula is something like this. It's very simple. So the resolution is given by square root of G times lambda. So this is the resolution. So this for the proximity printing. So the third one is the projection lithography. We will focus on this one because this is the method used for the production. of the semiconductor devices for the IC manufacturing. So in this case, you can see, so the mask is on the other side of the resist. So the resist will never have a chance to contaminate or damage the mask. So the mask can be used for many, many times. More importantly, because we use the lens, to project image from the mask onto the resist, there can be some deduction. Because we can have a demagnified image. For instance, if the structure here is, say, 360 nanometer on the mask, then the feature size on the resist can be 90 nanometer. So that means, so here we have 4 time reduction. So when we have this 4 time reduction, it will be easier to make the photomask because the feature size on the photomask is 360 nanometer, easier to make than if you have to make a photomask of 90 nanometer. So now let's look at the light source for the optical lithography. For the lab equipment, the most popular light source is the Mercury Arc Lamp, but actually at the moment, it's also possible to use LED UV light. So LED UV light is also available for the photolithography. For the Mercury Arc Lamp, so we have a glass container. We have the mercury vapor inside. Then we apply a high voltage, and then it will form the plasma. So there will be arc. Discharge of the mercury vapor form the plasma. So we have the plasma, electron and the ion. They are excited. So when they come back together, energy, the light will be released when the electron and ion they recombine. So this is actually is also used for the lightning. For the lightning, we know we use the CFL. Right now we use a lot of right now we mainly use LED light, but actually before this we used a lot of the CFL, compact fluorescence lightning. This one is also used the Mercury arc. So we have the mercury vapor inside the CFL light. Then we put some fluorescent material on the glassware to convert the UV light into the visible light. So here is the spectrum of the Mercury arc light. So as you can see, we have the I line, which is 365 nanometer. We have H line for 5 nanometer, and the G line for 36 nanometer. So those are the UV light we use. Those are the UV light we use for the lithography in the university labs. So we normally use I line and H line. Sometimes we use the G line. So, but when we want higher resolution, we need to go to the smaller feature size, smaller wavelengths. But for the case of smaller wavelengths, this is the Mercury Arc Lamp. You can see for 248 nanometer, the light intensity is very low. So we need to look for another different light source that has higher light intensity at shorter wavelengths. Here it's for 248 nanometer. So this is the case for the excimer laser. So we use the excimer laser to generate light at shorter wavelengths. So those wavelengths is called deep UV. So what is the excimer? So excimer means excited dimer. It has two components. One is the noble gas, another one is hydrogen. So we know that the noble gas is very inert. It will not form a compound with other materials. So the noble gas is, will not form a compound with the hydrogen. But when they are in excited state, actually the noble gas and hydrogen, they can bond to form a compound. But this compound is not, stable. It's not stable. It will fall apart. But when they fall apart, it will release the deep UV light. So first, we need to provide energy to bring those elements to the excited state. So that means we have the plasma. The plasma provides energy to go to the bonded state. So here is the example of the xenon chloride excimer laser. You can see we have xenon chlorine. They will form xenon chloride at the excited state. But this excited state is not stable. It falls apart. This will release the deep UV light. Then this is the ground state. For this ground state is not stable. It will fall apart to form the xenon and chlorine. So for the case of the xenon chloride, the wavelength is 308 nanometer. For the case of the krypton fluoride, the wavelength is 248 nanometer. So in this case, the excitation has to be paused, because otherwise the energy will be too much. Everything will get melted. So this is the pulse. So the laser is nanosecond pulse. That means for deep UV lithography, actually we use laser pulses to expose the resist rather than using continuous wave light. So this is the reaction for the krypton fluoride. This is for argon fluoride. Argon fluoride gives wavelength of 193 nanometer. But this one is used for today's IC manufacturing. Today's IC manufacturing, we use 193 nanometer immersion lithography, and we also use EUV. This is the extreme UV light, which is 13.5 nanometer. But we still use a lot of 193 nanometer. So now let's look at the photomask. So photomask, we need some area to be transparent, the other area to be opaque. Normally it is made by chrome on top of soda lime glass or on quartz. The soda lime glass is cheaper than the quartz, but quartz has lower thermal expansion, and this the quartz is used. The quartz is used for the IC manufacturing. So why we use chrome? The first, chrome is very stable. It will not get rusted. We know that for the iron gets rusted in air. For the chrome, it will never get rusted. Actually, if we add chromium to the iron, then we have the stainless steel. Secondly, chrome is very chemically stable. So no acid or no base can etch away the chrome because it forms very dense chrome oxide on the surface. So chrome can be etched by compound etchant, but not by a single acid or single base. If the resolution is low, you can also use the transparency. Transparency, you print some black ink. Your laser printer print some black ink pattern on top of the transparency. It can also be used as a photomask. The polarity of the photomask, it can be a light field, that means most area is transparent. It can also be a dark field, most area is opaque. Whether you use light field or dark field depends on what pattern you want and what resist you want, the positive resist or negative resist. So now let's look at how to make the photomask. So the photomask is made by the laser beam writing. So laser beam writing. This laser beam writing can give you the feature size below 500 nanometer, maybe say 360 nanometer, for example. So we know that for the 360 nanometer, this can be used to give a structure of 90 nanometer after photon reduction. If you want even higher resolution, you have to go to the electron beam lithography. Electron beam lithography will be much slower than the laser beam writing, but it gives you higher resolution. So here the process is simple. So first, you have the resist on chrome and on quartz. Then you use the laser beam. This focus the laser beam. That is focused to a few hundred nanometer. Then you do the exposure, you do the development. Then you use the resist as the mask to etch into the chrome. Finally, you can remove the resist to have the chrome mask. But this is the way you make the photomask. So you can make the photomask at the University of Waterloo, a quantum nanofab, because we have the laser beam writing in the clean room. So normally the cost to make a photomask for the research is about $200. So this is the sniper schematic of the sniper. So here we have the light source, and then we have the shutter. So when we do the alignment, when we move the wafer, we need to turn off the light. This is done by the shutter. Then we use the alignment laser the laser will align the photomask with the wafer. This is the alignment laser. So here, then we have the reticle. The reticle is actually a photomask. It's just photomask. But for the semiconductor industry, they call the photomask as the reticle. Then you have the projection lens, and you have the stage. You have the stage movement. So you do this die by die. It is a die by die process. So this is called a sniper. So what limits the resolution? So the resolution is limited by the light diffraction. So when we have a small aperture, for example, so when the plane wave comes in, ideally we got the profile something like this, light profile something like this. But because of the diffraction and the interference of the diffracted light, we get the light profile something like this. So this is the near field. This is the near field. So this corresponds to the situation for the contact and the proximity printing. When you go to far away, very far away, this is the far field. The far field can be many centimeters. So this corresponds to the case of the projection printing. So for the projection printing, so it is far away. Then we have the lens. We form the image on the photoresist. So now we look at this. This is the part. So what do you see here? You see that so we have the maximum. This is the peak. Then we have the minimum, the maximum, minimum, maximum, minimum. So you can see, so when the light pass through the aperture, so we have this central maximum, then we have another maximum, minimum, maximum, minimum, as you see here. So maximum, minimum, maximum, minimum. So the same as here. So maximum, minimum here, minimum, maximum, and minimum. So then for the size of the lens, the bigger lens you have, obviously the bigger lens you have, the higher order of the diffracted light will be captured. So those higher order diffracted light carries the detail of the fine structure. For example, the edge, the edge of the opening is the information of the opening of the edge opening is carried by this higher order diffracted light. this is like a DC light. It does not carry the detailed information. So the bigger the lens you have, the more light you get collected, you get finer, higher details of the opening on the mask. So how big? So how to determine how big is the lens? So normally we know the lens determined by the diameter, but actually the effect of the lens to collect the light is determined by the parameter called numerical aperture. Numerical aperture. So numerical aperture is defined as the n sin alpha. N is the refractive index of the medium here. If the medium here is air, n equal to 1. If the medium here is water, n equal to about 1 to 1.5 for the UV light. But for the for the visible light, the water is 1.33. But for the UV light, the index is higher. So here we say that the size of the lens, the capability for the lens to collect the light is determined by this numerical aperture n sin alpha. So ideally, when we have the point source, after the two lenses, it will also become a point source. This is the parallel light. So when the when the plane wave comes onto the lens, it will form a single spot. But in reality, because of the diffraction, actually the light here is not a geometrical zero-dimensional spot. It is a pattern. So this is called area disk. So we have the central maximum, then we have the minimum. So we have first minimum, then we have the maximum here, then we have another minimum. So this first minimum is given by 1.22 lambda f over d. So lambda is the wavelength, f is the focal length, focal length, d is the diameter of the lens. As you can see, the bigger the lens, more light gets collected. The smaller of this central spot is closer. It will be closer to the single point image. So now let's look at what determines the resolution. So the resolution, is a kind of arbitrary. It depends on many properties. The property of the lens and also the property of the resist, the property of the exposure systems. But to make it simple, the Lord Rayleigh, he proposed a resolution criteria. It's called a Rayleigh criteria. In the Rayleigh criteria, it says that how small, how close A prime and B prime, how close those two spots can be formed on a resist image, that they can still be resolved. But he said that when the minimum of the first peak overlaps with the maximum of the second peak, we said that those two spots they can just be resolved. So the light intensity profile will be something like this here. Will be something like this. Go down, go up. This is the light intensity profile. This is the Rayleigh criteria. You can see this image. So here, the separation, the distance between the two central part is bigger than this R. So it's well resolved. But when they're smaller, when the distance between the two spots is smaller than this R, it is not resolved. So when they are equal to the R, we say it is just resolved. So the resolution, the separation between the two spots is given by resolution 1.22 lambda f over d. You can see it here. So 1.22 lambda f over d. So we can do some change. So here the d. So here first we put the index. For the case of air, this is equal to 1. But if they are not air, we need to put this refractive index here. For the case of d, the d is diameter of the lens. It is equal to f times tangent alpha angle. So when the alpha angle is 2 times f times tangent alpha. So when this angle is small, the tangent alpha is similar to the sin alpha. So that means we have the 2 times f sin alpha. 2 times f sin alpha. The f cancel out, you get 0.61 lambda over n sin alpha. So n sin alpha, as we know, this is the numerical aperture of the lens. So equal to numerical aperture. So generally, this number 0.61 can be replaced by a factor K1. This is called K1 factor. So now let's look at whether this makes sense or not. So first shorter wavelengths, smaller r, higher resolution. So this makes sense. Secondly, bigger numerical aperture, bigger length give you smaller feature sets, that is higher resolution. So the factor of K1 contains the information of the all other factors, including the property of the resist, exposure system, how you do the other tricks to improve the K1. So we will look at the K1 next lecture. So here is the imaging examples for the optical lithography. So in the here is 248 nanometer, and we know this corresponds to the laser sort of krypton, KRF. This is the krypton fluoride. This corresponds to the krypton fluoride. So you see it's blurred. The numerical aperture is 0.7. When the numerical aperture becomes 0.8, it's better. So this one is argon fluoride. Shorter wavelengths, you get better resolution. Here, numerical aperture 0.68. We have higher numerical aperture, you get better resolution. So even higher numerical aperture, better resolution. 0.93 is even better resolution. So this is the maximum numerical aperture you can get in practice. So in theory, you can get numerical aperture to be 1, but in reality, you can get maximum 0.93 numerical aperture. So this one is 157 nanometer wavelength, so shorter wavelength. This is also excimer laser fluorine excimer laser. You get better resolution. So when you do the immersion, so we know that for the air, the numerical aperture maximum value is 1. But when you do the immersion, numerical aperture which is equal to n sin alpha, if the index refractive index is much higher than 1, you get numerical aperture higher than 1, you get better image. For today's lithography system, we use the immersion lithography and argon fluoride. If we go to even shorter wavelength, 13.5 nanometer wavelength, you get much shorter wavelength compared to this 193 nanometer. You get much clearer image. So this is the case for the extreme UV lithography. So we will talk about extreme UV lithography in this course. So now let's look at the property of the photoresist. The photoresist is a liquid mixture that can be spin coated onto the substrate. So the resist contains 3 components. First is the background material. Background material is also called a resin, a binder that provides mechanical property, adhesion, and other properties. Then we have something sensitive to the light. The material sensitive to the light is called a photoactive compound. The third component is the solvent. So we need to dissolve the resin and the sensitizer into the solvent to form the liquid. Then we do the spin coating to get the resist film. So there are 2 types of the photoresist. The first one is called a positive resist. For the case of positive resist, exposed area will become more soluble by the developer. For the negative resist, exposed area will become less soluble in the developer. Those areas will be developed, but this area will remain. So here, this area will be developed. This area will remain. So now let's look at positive resist. So most popular positive resist for the I line and the G line and also H line, which is 4.5 nanometer. H line. This DNQ is the most popular resist for the I line, G line, and H line exposure, but it does not work for the 2 short wavelengths. For this DNQ resist, it contains this one, diazo-naphthoquinone. This one, diazo-naphthoquinone. This is the photoactive compound. So the resin is Nova-like. This is the Nova-like background matrix material. This is called Nova-like. This one is a polymer. This one is a polymer. This one is a molecule. So you can see that for this polymer, we have a lot of hydroxy group. So this one in the solution, it will release is like an acid. So this material, Nova-like, is soluble in the base developer. It is soluble in the base, like the QH or sodium hydroxide, soluble in the base. But this material is not soluble in the base developer. As a result, so when you mix this material with this material will also become insoluble, because this material will act as an inhibitor. This will reduce the dissolution rate of this material in the base developer. Right? In one word, in one sentence, in short, so when you have this film together, the two materials come together, they will not be soluble in the base developer. So now let's look at what will happen when the light shines on. So here you can see we have this group, N2 group. So this one is something like N, another N, a 3 bond, N2 group. So when you shine the light, so this part, there will be some chemical reaction of this part. So when you shine the light, so this part, this bond will get broken. This bond gets broken. They leave behind two unpaired electrons. So this structure is not stable. This is not stable. So they will be rearranged. This is called a Wolf rearrangement. So here the carbon from here will come up. The carbon from here will come out to form this structure. So because the exposure is done in the air, so there will be some water. There will be some water molecule in the resist. So when there is water, this part will become this one. So this is the carboxylic acid. Carboxylic acid. This is what you can imagine. This is the acid. So the acid will be soluble in the base. So you have KOH, NaOH, or TMH. This acid will be soluble. So you can see before exposure, so this part is not soluble in the base developer. So after exposure, this material becomes soluble in those base developer. As a result, this will be a positive resist. So the net result is that the dissolution rate in the base developer is 100 times higher than before the exposure. So this is a very high contrast, a positive resist. So normally in the lab we use the KOH solution as a developer, but we know that potassium or sodium, they are not good for the semiconductor devices. So we want to use something that contains no metal. This is the case of TMH. TMH contains no metal. It is also a base. It is something like this. So we know about ammonium hydroxide. So this is the ammonium hydroxide. If the H here is replaced by the CH3 group, if this hydrogen here is replaced by this methyl group, then it becomes TMH. It is the tetramethyl ammonium hydroxide. Tetramethyl ammonium hydroxide. It's similar to the ammonium hydroxide, but this H is replaced by this methyl group. This one actually, TMH is much more popular than the KOH, because this one, as I said, does not contain the metal. Those alkaline metals is very bad for the semiconductor devices. So now let's look at a negative resist. For the negative resist, it will become insoluble after exposure. So normally the negative resist is a polymer with long chains. The molecular weight is 10 to the power 4 to 10 to the power 6 kilogram per mole. So the longer the chain, the higher the sensitivity, the less energy needed to expose the resist. So when you shine the light, the polymer chain will become cross-linked. It will become cross-linked. So once they are cross-linked, it will become insoluble in the solvent. So those solvents, like benzene, toluene, or xylene, they will dissolve the linear polymer, but not the cross-linked polymer. So this will act as a negative resist. So now let's look at the property of the resist. So what parameter determines the property of the resist? First is the contrast. The contrast is the property of the resist to distinguish between the exposed area and non-exposed area. So for the positive resist, we know that when we do the exposure, then we do the development. So the well-exposed area nothing will remain. So the remaining resist thickness will be 0. So non-exposed area, it will remain. So this is the property of the positive resist. Now for the negative resist, exposed area will remain, unexposed area, low dose exposed area will be dissolved. So we have this curve. So the slope of this transition area, determines the contrast. So ideally, you can imagine, we want something like this. Ideally, we want a sharp transition. We want a very sharp transition. Then we want something like this. From here, come down. This is ideal case. So here we have something like this. Here, come up. We have very sharp, very abrupt transition. In this case, you have very high contrast. But in reality, there is some slope. So here the starting point, here is the ending point. So the contrast is defined by this equation: 1 over log 10 df over d naught. For this case, the df and d naught, they are the same. So the df equal to d naught. Then this 1 log 10 1. This becomes 1. We know this is 0. So gamma equal to infinity. That means for the ideal case, we have infinite contrast. For your resist, we have a finite contrast. Typically, G line and I line resist, the contrast is 2 to 3. But deep UV resist, the contrast is higher. So another property is the sensitivity. How much dose we need? That is defined by this dF value. dF value is the dose we need to develop the resist to the bottom. For the positive resist. So the lower the dose, the better. So the unit for the dose is given by millijoule per square centimeter. How much energy we need per area of the exposure. So again, for the typical I line and G line resist, the sensitivity is about 100 millijoule per square centimeter. For deep UV resist, chemically amplified, the sensitivity is much higher. So another property is that the gamma, the contrast, and the sensitivity is not intrinsic property of the resist. It is the property of the resist, but not the intrinsic property of the resist, because other parameters will also affect the contrast and the sensitivity. For example, development time and baking temperature, all those things, they will change, they will affect the contrast and the sensitivity of the resist. Here's the summary of the property of the resist that we desire. The first is the resolution. Obviously, we want higher resolution, the better. Higher resolution means smaller feature size. Then is the contrast. So if you want higher resolution, we need a higher contrast to give you higher resolution. The third is the sensitivity. So normally we need lower exposure dose. So lower exposure dose means higher sensitivity. So this is determined by the quantum yield. Quantum yield is the number of the photon-induced chemical reaction per photon absorbed. This is the quantum yield. For the normal resist, the yield is less than 100%. But for the case of the chemically amplified resist, the quantum yield can be higher than 1. Then the etch resistance, because usually we use the resist as the etching mask. For example, if you want to etch a silicon with the resist, you want to etch into the silicon with the resist as an etching mask. You want the etching rate for the silicon very fast. You want the etching rate for the resist very slow. That means the resist should be very resistant to the etching process. This is why it is called a resist. Unfortunately, for the case of the Nova lac, this Nova lac contains lots of this benzene ring phenyl group. This phenyl group is a very stable chemical group, so it is very resistant to the etching process. So normally, we have the benzene ring phenyl group, and we have less oxygen. If we have less oxygen in the polymer chain, in the polymer structure, then the etching rate will be slower. So in the end, this is the typical photolithography process. So first, you need to prepare the surface by surface cleaning by the solvent or by the RCA cleaning. You can also do the baking process to drive away the water vapor on the wafer, to drive away the dissolved water molecule on the wafer surface. Then you can apply the HMDS. If you want high resolution, smaller feature set, you need HMDS because this will promote adhesion of the resist onto the wafer surface. But here it says it's done on the semi-coating, but actually spraying HMDS on top of the wafer is not the best way. So the best way to apply HMDS is to do the vapor coating onto the wafer surface. Then you coat the resist by the semi-coating process. It can be 0.5 micrometer or a few micrometer or a few hundred nanometer. Then you bake it. During the baking process, you get rid of the solvent. By the baking process. If you bake in the oven, you need tens of minutes. But if you bake in a hot plate, on top of a hot plate, you need just a few minutes. Then you do the alignment and you do the exposure. The dose, as I said, is about tens of to hundreds of millijoule per square centimeter. Then you can do the post-exposure bake. But this is not always needed. But if you do the chemically amplified resist, so when you do the chemically amplified resist, you have to do the post-exposure bake. Then you develop the resist. If you want, you can do the post-bake. You post-bake the resist. This one is done at higher temperature for a longer time. So this process will make the resist harder. If you want to use the resist as an etching mask, you can do the post-exposure bake to make it more resistant to the etching process. But finally, let's look at the semi-coating process. So in the semi-coating process, so we apply the resist on the liquid resist on the surface. Then we do a faster semi-coating. This way, you get very uniform film thickness. So the film thickness depends on the spinning speed and also the setup of the semi-coater. So what's the unit for the spin speed? It is RPM. Resolution per minute. So normally the semi-coating is done at over 2000 RPM. 2000 resolution per minute semi-coating to get the film, to get a uniform film. Okay, thank you.